An epicycloid is a shape that's formed when you have a circle and a second circle. It's usually smaller than the first circle, but doesn't have to be. And that second circle is rolling around the other circle. It could be moving, it could be going clockwise or counterclockwise. And it makes a shape. If I take a point on it, like this red point, it kind of makes, actually I'll start with this red point. It makes a bunch of sort of things that look a little bit like cycloids. Kind of like that. And sometimes it doesn't overlap and you get something like this. It becomes a cool looking like flower shape. Anyway, I'm going to show you in this video how to find the equation of an epicycloid if you know the radius of the circle that it's rolling around and the radius of the rolling circle, and whether the rolling circle is rolling clockwise or counterclockwise. But first, let's see a somewhat simpler question. Here's a circle. Here's a circle whose center is actually on the circle. The big circle has a radius of 10. The small circle has a radius of 2. And this is not rolling around the edge of the bigger circle. But this circle, this little circle, I'm going to call it, I'm going to say it's floating. It's floating. I'll have it, I can tell you whether it's floating clockwise or counterclockwise, so I'll say it's floating clockwise. But on it, there's a point which I want to put over here. And that point, just for whatever reason, is going counterclockwise while the circle goes clockwise. So this is going this way, but this point on it is going this way. And it's going to make some kind of thing. I don't know if I dare even draw. It's just going to make some kind of thing. I'm going to show you whatever it looks like. I'm going to show you how to find the equation of that thing. That equation, parametric equation, is going to have two parts. The part on the right here is the equation of the path of the center of the floating circle. And since that center goes around a path like this with radius 10, it's going to be 10 cosine and 10 sine. It's starting here at the 0 degree mark, so I don't need to put any sort of like plus after the t. But I am going to need to make the t negative, because if it was positive, it would go around this. It would go around this way as the angle got bigger. I'd go to cosine 1 degree, 2 degree, cosine 1, sine 1, cosine 2, sine 2, and so on. I need to go negative to make it go clockwise. Now, as far as the circle itself, the rolling circle, well, that is 2 cosine and 2 sine. Oh, I forgot to say a very important piece of information. Aside from these 4 pieces of information, the radius, and whether it's going clockwise or whether it's going counterclockwise, whether the center is moving around the big circle clockwise or counterclockwise, whether the point on the circle that's floating is going clockwise or counterclockwise, there's a 5th piece of information you need to know. We need to know how fast is this red point going around, and I'll tell you that for every 1 degree the circle moves, the point on the circle moves 5 degrees. They have to tell you that, because I could have a slowly rotating circle or a fast, quickly rotating circle. Well, that 5 ends up over there. And that's the answer to the question. This is a positive 5t because the point on the little circle is going counterclockwise. If it was going clockwise, I'd have to have a negative 5t. Well, that's when it's floating. But that's not what epicycloid is. Epicycloid, it has to be, well, a couple of things. Actually, let me make another question with a floating circle. In this one, the circle's moving counterclockwise, and the points on the circle is also moving counterclockwise. And again, for every 1 degree, this is floating circle again. For every 1 degree, it rotates 5 degrees. So in this question, x equals, y equals, plus, plus, the path of the center, oh, and this is 10 and 2 again. So the path of the center in this case is actually going around a circle of radius 12, because out here, 10 plus 2. So it's 12 cosine t, 12 sine t. That's half the answer. This little circle is radius 2. This t is positive t because it's going counterclockwise. And this one's also going to be positive because the point on the circle is also going counterclockwise. They have to tell us that. And that's why it's 5t, 5t. Now let's get to the actual epicycloid itself. It's a little different. First of all, and this is something that's not like so obvious, but oh, in this case it's still 10 and 2. I want to make my center go clockwise. And it's hard to visualize this without me being able to sort of animate it, but in order for it to go clockwise, the point on it also has to go clockwise. That's how that happens. That's not going to happen for the epicycloid, but I'm telling you that in an epicycloid where it's actually rolling, like physically rolling, if the center of the circle is going counterclockwise around the center of the other circle, then the point on the circle will also be going counterclockwise. And if the center of the circle was going clockwise, the point on it would also be going clockwise. So what this means 2 cosine, 2 sine. It's going to be positive t, and it's going to be 12 cosine t, 12 sine t. But I'm not done, because there's a lot more going on inside these parentheses besides the fact that there's a t and that that's plus t. I think I'll use a real specific example here. So here I have the point that's going to be moving, and let's say I'm at a spot where this circle has rotated 40 degrees. The center of the circle is now 40 degrees. Now, a small circle going around a big circle is going to have to make a lot of revolutions to get around there. And a bigger circle has to make fewer revolutions. In general, if you divide the radius of the circle that it's rolling around by the radius of the circle that's rolling, that number is going to be really important. It's going to go here, but we're actually not done yet. You might think we're just done there, but we're not, because see, after 40 degrees, this this blue ends up over here. If I imagine this circle here is just kind of staying in place, but rolling at this, but rotating at the same speed as the one that's actually moving. So I would have like a 200-degree angle here, that blue arc. But what happens over here, when it rolls, it's true, I still have the 200 degrees, but it's 200 degrees. You see, this right-hand point, as this thing rolls, this right-hand point is kind of like my reference point. It's horizontal in the beginning. It ends up over here. So the location of this green point here is not 2 cosine of 200, because 200 is over here somewhere. You see, we don't measure the angle with relation to where the red point is just because it used to be horizontal. We have to measure it with relation to what the actual horizontal is over here. So I have to measure this angle. And to do that, I need to know the measure of this angle right here. Well, I didn't draw it so well, but that angle's 40 degrees because these are parallel, they're both horizontal, and corresponding angles makes them both 40. So this point is actually located at the 240 degree spot, and that's why for the epicycloid, and this is sort of main takeaway, it's not 5t. It's 5t plus extra t, which is 6t, but I'll leave it as 5t plus t. That plus t is what you do, and that's always going to happen in the epicycloid question. Without the plus t, it's a little bit off, and that's how the epicycloid works.